Okay, now it's going. So, alright, start with some basic stuff. The outline of how this course is going to go roughly is we're going to start by developing logic. Then we're going to develop set theory. Then we're going to have a weird, it's like chapter 0 in the book, which is just going over a bunch of notation, basically prerequisite material that the author needs you to understand before you go through it. So just prereq stuff. And then we'll actually start the topology. This is the way it's going to work. So we're going to build it from the ground up. All the videos I record, I'll have a playlist on YouTube. Just search my name on YouTube. There'll be a playlist called Topology. All the videos will be uploaded. There's no reason I shouldn't be able to have them uploaded by the end of tomorrow. So you'd have to wait at most a 24-hour period for them to be uploaded, I think. Who knows? Crazy stuff could happen when the internet goes down. The book, here's the ISBN. If you care about the book, I didn't suspect most people would really care about having a book. I think most of you are just going to come here, try and absorb the lecture the best you can, ask questions and move on with the material. But if you do want it, there it is. It will be a little bit before that becomes necessary, so plenty of time to order it, get it. If you plan on purchasing the book, there's a website called bigwords.com. It's a middleman website that searches a bunch of websites for you to help you find a good price on the textbook. It's the website I used for all the textbooks while I was going to college. Since a few of you are students I haven't had before, go over some basic stuff that I go over with new students every time I have new students. First thing, this book I'm teaching you, this topology course I'm teaching you, how am I so qualified to teach this to you? I took it once as a class. That's how. What do I mean by that? I mean, how prepared do you feel to teach Algebra 2? Not? Probably? Okay, so now you know the boat I'm in. So when I put something up on this board, there's no reason for you to just accept it. There's no reason that I didn't make a mistake. If I interpret something one way and you interpret it a different way and it's different from mine, point that out. There's no reason that your way of seeing it is inferior to mine for any reason. I'm not an expert on this stuff. Part of the reasons I'm teaching this is because I just want to go through it again. I want a better understanding. So that's one of the reasons I'm teaching this material. So be critical of everything I put on the board is essentially what I'm getting at. And with this many people being critical of what we put on the board, if we're all thinking about it, it's very unlikely that something that's false should be able to stay up there for an extended period of time, right? Mm-hmm. Right? Yes. Right? Yes. That's another thing I'm going to do. If you don't respond, I'm just going to yell more and more. More and more!
Fair enough.
Fair enough. I'll take that as a response. Okay. So, let's see. Other basic bookkeeping stuff. Those of you who have taken classes with me, think we're just ready to go?
Yeah.
Yeah? The eyebrows are going up. I guess we'll take that as a response. Okay. And the late students are here.
You're welcome.
Well, you got here just in time. We're now ready to start the material. ISBN, if you're going to get the book, is right here. Bigwords.com is the website I recommend if you're going to do it. Wow, a lot more people are doing this than I thought would do this. Crazy. All right. So we're going to start with the development of logic. We're going to start with propositional logic. And for those of you who just did logic with us, we're not going to come at this from the sentential way. Well, you'll see the difference. We'll just start getting into it. So propositional logic, it all starts with a proposition. What's a proposition? A proposition, we'll use P to represent it. A proposition P is a variable whose value is either true or false, not both. So as we're developing propositional logic, we are not interested in this class in determining whether a particular proposition is true or false. We just take propositions that we know are true or false and determine what else is true for them. So for example, the statement, the sky is blue, is a proposition. That's either true or false. Now, whether it's true or false, that's a question for science. But the statement, the sky is blue, is a proposition, and we can apply propositional logic to it. It is something that is either true or false. 2 plus 3 is equal to 19. That is a proposition. We happen to know that's a false proposition, but that's still a proposition. The typical way that you're introduced to this is they give a definition of a statement, a sentence that's either true or false, a statement. Everything that's a statement, for the purposes of this class, we can say is a proposition. Something that's true or false. Good?
Yeah.
Nothing weird about this definition? Alright, moving on then. We have two special types of propositions. A proposition that is always true, we call a tautology, and one which is always false, we call a contradiction. Right? Some quick examples of those. Let's look at the common one for tautology is the sky is blue or the sky is not blue. There's a tautology. That statement's always true. If the sky is blue, that statement's true. If the sky is not blue, that statement's true. In either case, the statement's true. The sky is blue or the sky is not blue. That whole statement together is always true. That's an example of a tautology. An example of a contradiction would be the sky is blue and the sky is not blue. Contradiction, always false. The answer is 6 and the answer is not 6. Example of a contradiction, always false. So tautology, it's always true. It's true independent of what the variable, oh, we're not talking about variable yet, sorry. It's always true. If it's a proposition, that's always true. Tautology, if it's a proposition, that's always false. It's called a contradiction. Okay. So now we're going to look at how to get new propositions from existing propositions with operators. We're going to call them logical operators. If the operator happens to only take one proposition, we're going to call it a unary operator. If it takes two propositions, we're going to call it a binary operator, etc. Tertiary operator takes 3, you go from there. Now, what do operators do? Operators take in something and give you out another, well, let's look at a particular example. Let's look at a unary operator on the numbers. Give me one. Square root. Okay, square root is a unary operator on the numbers. You give the square root operator a number and it spits out another number, right? You give it 16, it spits out 4. Yeah. Mm-hmm. You give it 4, it spits out 2. So we're going to create some unary operators on propositions. I might accidentally call these booleans. If I say boolean, I'm just talking about proposition. That's computer science terminology. So a unary operator on a proposition, we're going to develop 4 of those really quick. Because notice that if I give, so now we're in a world of these propositions. It's like we're in a world where we only have 2 numbers. And we're creating operators in a world where we only have 2 numbers. Because I can only turn trues into trues or falses, and I can only turn falses into trues or falses. All we have are propositions. So every unary operator that we apply to a proposition still has to spell a proposition. So it can only take in true or false values, and it can only spit out true or false values. Does it make sense what I'm trying to say?
Yes.
Yeah. Okay. So notice that based on true or false, there's 4 possible combinations of how we can spit out. Right? I can make so that if you give me true, I spit out true. And if you give me false, I spit out true. I can make, no matter what you give me, I always spit out false. I can make whatever you give me, I spit out the same thing. So if you give me true, I spit out true. If you give me false, I spit out false. And I can make so if you give me true, I spit out false. If you give me false, I spit out true. So these are all the possible ways that we can define a unary operator, and we're just going to come up with a definition for each of these cases. So let me just write it, and then let's refill it out. Do 1 at a time, because I think I'll lose you doing 4 at a time. So let's start with the simple one that y'all know. What's a unary operator that y'all know?
Square root.
Square root.
On
No.
logic.
No.
On logic.
No.
Not. Not is a common one. So not is that one, not x. That's how we write not x. Now, if x is true, then not true is false. If x is false, then not false is true. So not happens to capture this operator. Now say the operator that doesn't change anything. You give it true, it spits out true. You give it false, it spits out false. We typically call that the identity operator. So we might use ID on x. Something like that. Then, if no matter what you give it, it spits out true, then it's turning your proposition into a tautology. So we might call this the tautology operator on x. And then if no matter what you give it, it spits out false, then it's always spitting out a contradiction, so we might call it the contradiction operator on x. Right? So these were all the 4 possible combinations, and then I can just start naming those 4 combinations, give them some name, some symbol to represent that operator. There we go, we have a new unary operator. In practice, here's the only one we really care about, the not operator. But the point is, we could have taken any 4 of these operators, any 4 of these combinations, just given them a name. There we go, we just defined a new unary operator, right? Yeah. So, now let's look at a binary operator. With a binary operator, it's going to take in 2 propositions, right? Yep. And there's going to be 4 combinations on how it can do that. If I have a binary operator, I can give it true and true, I can give it true and false, I can give it false and true, I can give it false and false. Maybe before we develop a logic one, let's think about a binary operator that we all know and love. Addition. Addition is a binary operator on the real numbers. You give it 2 real numbers, it adds them together, it spits out 1 real number. Any binary operator that we have on propositions is going to take 2 propositions, somehow put them together to spit out just 1 proposition. Right? And that's what we mean by binary operator. Each of 2 propositions spits out 1. Okay. So, there's 4 combinations. How many possible binary operators could we define? No.
Oh, 16.
16. There's only 16 columns we could possibly make of T's and F's, right? Because each column is going to have 4 T's and F's. For each one I have 2 options. Do I use T or F, T or F, T or F, T or F, 2 times 2 times 2 times 2, 16. But there's only so many binary operators that we care about. So we don't care about all the 16 binary operators that we can make. We're not going to write them all out, and we're not going to name them all. We're going to pick a few that we think are useful, name them, and just use those. Make sense? Okay. Now, whatever we put in this column, when I fill out this column, this is going to be the definition of this operator, the same way that not was the definition of these operators. However, we're going to tie it to English words to help it appeal to your intuition so that you intuitively know how to use the operator, like we did with the not. You know, not true is false by definition of the not operator, but you also intuitively know if something's not true, then it's false. And if something's not false, then it's true. So we're going to do the same thing here to define these different operators, but what we have on this truth table is their definition. We're just now going to try and connect our intuition for to the definition. So this first operator, that little wedge right there, upside down B, is called the AND operator. And it ands 2 propositions together. In terms of sentences, we call this a conjunction. So if I know that statement A is true, and I know that statement B is true, what do I know about A and B?
It's true.
It's true. Sorry, I said A and B, we have X's and Y's. If I know X is true and I know Y is true, then X and Y is true. Right? If it's true that Rhoda was late for class, and Emma was on time for class. If those 2 statements are both true, then we know that the conjunction of them, Rhoda was late for class and Emma was on time for class, is true. Right?
Yes.
And we could even do a quick little proof to show that that's the same as Y and X, also true. So, you can, maybe we won't talk about associativity so soon, or commutativity. Never mind on that last point. Okay, so let's move on. So now we have this case. So we're saying, what if X is true and Y is false? Then X and Y is?
False.
It's false. Does that appeal to everyone's intuition, or do we need more explanation? let me specify for those of you who are new, if you feel like most of the class here is just getting this easy, that's because I've gone over it with them 10 times. Okay? So if something feels fast to those of you who are new, say stop, slow down, whatever you want. There's no point with me preparing all this stuff and presenting it to you if you're just going to let go over your head. So don't waste my time. If you have a question, let's bring up the question. If something didn't make intuitive sense, let's make it make intuitive sense. Okay? So next one. If x is false and y is true, then x and y is
False.
false. And then finally, if they're both false, then it's true.
False.
Right? No! It's false.
I heard that, Peter.
The conjunction of two false statements is false. Did I get Peter to say true or yeah or something?
He doesn't.
Alright. So, there's the AND operator. Now, the next one that we're going to talk about is the OR operator. And we always need to make a note that we use OR two different ways in the English language. And so it's hard to make the intuitive connection to the logical OR that we use. So what are two ways that we use OR in the English language?
This or that.
Well,
Like
we have one case where it's A is true or B is true, but they're not both true. And then we use OR to mean at least one of them is true. So let me give you the two sentences. Someone says, where's Donnie? And you say, he's in room 5 or room 6. What do you mean in that context? You mean he's in room 5 and he's not in room 6, or he's in room 6 and he's not in room 5. You don't mean it's possible that I'm in both. But on the other hand, if some university has some admission standard and they say you have to take calculus or physics, they don't mean if you take both you can't show up. They mean you have to take at least one of them. So that second sense is what we mean by the OR in logic. The OR of logic, we call it the inclusive, because it includes true in more cases. So this is the inclusive OR. Alright, so let's continue. So if I know that x is true and y is true, then x or y is true. Alright, if x is true and y is false, x or y is
true.
You sure?
Yeah. Why is that?
Why is that? Okay, let's explain.
Yes.
Good. So let's make x the proposition. I'm holding a red marker.
Okay.
Blue the proposition, or y the proposition. I'm holding a blue marker. Set up this case. So we're setting up the case. I'm holding a red marker as true. I'm holding a blue marker as false. Now this whole statement we're analyzing. I'm holding a red marker or I'm holding a blue marker.
I see. So it's like the blue sky one you mentioned before. Since one of them is true, it's all true.
Yeah. All you need is one of them to be true, and they're true.
Because it's the whole statement.
Yeah, one way we think about that or is at least one of them true, then it's true.
Okay. Got it.
Good? Alright, next case. Huh?
So that means that one's true as well.
Yeah, so the next one, true. If at least one of them is true, the whole thing's true. And then finally, if they're both false,
Then they're false.
then it's false. Wonderful. Okay. Moving on to this.
What is that sign?
Yeah.
Yeah, those of you who have taken logic before haven't seen this.
You got it.
The actual.
This is the same as the AND symbol with a vertical line through it. We call this NAND. And starting with an N. Laugh all you like. That is what it's named. It is named the NAND operator. What does it mean? It means not and, not both. NAND.
Okay.
Alright?
So it's
Then wouldn't it be the
excluding
same
instead
as
of
or?
including.
Let's see.
Not. Okay.
NAND means not and or not both. And meant they're both true, right? NAND means they're not both true. Okay, so let's look. If x is true and y is true, x and y is false.
Oh, so it's just opposite and.
And then if x is true, y is false, we have true.
Why not? False.
NAND means not both.
Okay.
Are they both true?
Then it's
No. So it's true.
that's messed up.
Not the or.
There were some implied ors in there. There were some implied nots.
No, it's the
So-
opposite.
NAND means not both. Is it true that they're not both true? Yes. That's how you would have to ask that question.
Yeah.
Alright?
Okay, yeah.
Man.
So, once again, if I have false and true,
It's true.
it's true. If I have false and false, it's true. False, right?
False, because they can't.
No, it's true. Good.
Right, they both have to be.
Not and.
Are they both true?
No.
So they're not both true. Good. Nand, not both. Not both? Yes, not both. It's weird. It is weird. You just got to make it quick. Notice that Nand is the negation of and. When and is true, Nand is false. When and is false, Nand is true. That's why we call it Nand, because it's a negation of and. Similarly, when you have an or symbol and you put a vertical line through it, what do you think this is? Nor? No. This is the exclusive or. So this is the exclusive or,
Where you can only be in one situation.
where one and only one is true. Not both, not neither, one and only one. So this is at least one is true, this is one and only one is true. Right?
One and only one is true.
Uh-huh.
So, it's
So
either
when you
one-
said Donnie's in room 5 or Donnie's in room 6, you meant that in the exclusive or sense. You meant I'm not in both rooms, and I'm not in neither. I'm in one and only one of those two rooms. So we call this the exclusive or. If we have to write it on paper, we typically just write X or.
Okay.
So I might accidentally say XOR instead of exclusive or just because common terminology. So the XOR, let's fill it out. If I have true and true,
False.
true XOR true is false. Remember, XOR is one and only one. If I have true and false, XOR is
True. True. False.
wonderful. Okay. Now the hardest logical operator to get intuition for. And this one, we will make sense of it here in class. Next week, you'll get confused by it for those of you who haven't come across it 10 times. And those of you that have, if you're still screwing up, I might throw something at you. Who knows? Okay, so this is called the implies operator. X implies Y. Another way that we might read this is if X is true, then Y is true. Or X is true only if Y is true. Or Y is true if X is true. Or X implies Y. I'm always going to read it this bottom way. X implies Y is how I will read that. We'll go over some sentences to show you how these are all saying the same thing. But first, let's write it down. Now, the hard thing about the implies is you want to use your knowledge about the way that this universe works to make sense of implications. Mathematical statements, all the statements that we prove here, are going to be true. What's the right way to say this? All the validity of math is completely independent of this universe. So it should no way be contingent on this universe to determine the truth or falsity of a mathematical statement. That's maybe how we can say this. So let's just start filling it out and see where we get stuck and go from there. So, well, now let's get our hands on vacuously true first. So first off, the left-hand side of an implication we always call the antecedent. The right-hand side we call the conclusion. And so we need to understand what we mean by a vacuously true statement. If I start any statement, any implication with, if Donnie's a purple dragon, then, it doesn't matter what you put after the then. Because Donnie's a purple dragon is false, then there's no cases to check. You can't see what's true if Donnie's a purple dragon. So if the antecedent is false, then the implication we say is vacuously true. If Donnie's a purple dragon, then Jacob's an elephant. True. There's no cases to check. The antecedent is false. It's vacuously true. Alright? So let's fill this out. If X is true and Y is true, then X implies Y is
True.
true. Wonderful. If X is true and Y is false, then X implies Y is
False.
false. Wonderful. If X is false and Y is true, then X implies Y is
True.
False.
true.
True.
It has a false antecedent. We call it vacuously true.
Vacuously true. You just
Vacuously
said if
true.
the first one's false, then it's all false.
If the first one's false, then the statement's true.
What's?
Alright, let's re-go through these real quick to help establish more intuition, this time holding up markers to make sure it makes sense. X was red, Y was blue, right? I'm holding a red marker, I'm holding a blue marker. And then we'll phrase it this way. If I'm holding a red marker, then I'm holding a blue marker.
True.
True. In this case, it's true. Okay. Next case. If I'm holding a red marker, then I'm holding a blue marker.
False.
False. So that's good intuition. If I'm holding a red marker, then I'm holding a blue marker.
True.
True. There's no cases to check. I'm not holding a red marker. Now, you might be tempted in your head to think, yeah, but you could, based off the laws of physics of this universe, I could bend down, pick up this red marker, and change the system. You're changing the system. So when I hold a red and blue marker, imagine that the whole universe is me holding these. There's no such thing as time, space, change, nothing. It's just the system you see before you. Me holding markers. Okay? So let's go over this example. If I'm holding a red marker, then I'm holding a blue marker. Is it false? No, it's not false. Then it's true.
Okay. Okay.
We making the connection? And then the last one. If I'm holding a red marker, then I'm holding a blue marker.
False.
True. There's no case. One of the ways that when I was learning it helped me connect with my intuition is I'd ask myself, is it false?
Yeah.
If I'm holding a red marker, then I'm holding a blue marker. Is it false? No. Then it's true. That's what not false means.
Okay.
Remember our definition of not? Not true is false, and not false is true. By definition. So true and true. So those will be confusing. You'll understand those for a second, and then the next second, you'll forget it. And we'll go over that 3 more times throughout this class. No question. Alright, so let's connect it with the if-then statement. What are the statements that help it make sense that these are all the same?
What?
If there's smoke, there's fire. That's what it is. Okay, this is one that helps it make sense to the kids' intuition. So we're going to make sense in our head that all these are saying the same thing, because you need to also be comfortable with the language that's used around implications. Because every theorem in math is just an implication. That's what it is.
Wasn't it oxygen and fire?
Yeah, it was.
Oxygen and fire. If there's fire, then there's oxygen. That's good. Okay, if there's fire, then there's oxygen. So X is, there's fire. Y is, there's oxygen. So is it true? Well, we're going to see that all these are logically the same. There being fire implies there's oxygen. If there's fire, then there's oxygen. There's fire only if there's oxygen. There's oxygen if there's fire. You see how it's the same as if there's fire, then there's oxygen. There's oxygen if there's fire.
Okay.
It's weird the first time you come across it, but you got to connect it with the sentences because who knows how I'm going to say it. And then finally, there's fire implies there's oxygen. If there's oxygen, then there's fire. There's fire only if,
Yes.
Yeah,
You mixed
fire
the first
only
one.
if there's oxygen.
You mixed up the first.
if there's fire, then there's oxygen. There's fire only if there's oxygen. There's oxygen if there's fire. There's fire implies there's oxygen.
X equals 5.
Need to use O's and F's so I don't get confused. Okay, so that's the implication. And then this last one we call logically equivalent. When is it true that X is logically equivalent to Y? When they have the same value. If they're both true, they're logically equivalent. If they're both false, they're logically equivalent. Otherwise, they're not logically equivalent. They're logically equivalent means that they have the same value. It's almost the same way that we use equals in math. When do I know that something's equal to 6? When it's 6. Right?
Yeah.
So only true can be logically equivalent with true, and only false can be logically equivalent with false. Alright, maybe I'm hitting the stress in too hard, and you already understand. So is true logically equivalent with true?
Yes.
Yeah.
Yes. Is true logically equivalent with false?
No.
Is false logically equivalent with true?
No.
Is false logically equivalent with false?
Yes.
Yes. Okay. So that's that. We already kind of mentioned on this note. How do I prove? So theorems are always implication statements. And what it means to prove a theorem is to show that a certain implication is a tautology. What's a tautology?
Something that's always true.
A statement that's always true. Proposition, I guess, is what we're using here. That's always true. That's what tautology is. So what's a theorem? The theorems are always in the form of an implication. How do we know we've proven a theorem? We know that we've proven a theorem if we've shown it's a tautology. It's always true. Okay. So let's do some basic, well, now you can't see how these are theorems because they're 2 and 1. I shouldn't have stressed that theorem is an implication so hard. We'll come back to it. We'll say for now, to show something's a theorem, you just show it's a tautology. That's why I worded it this way. I should have just followed my wording here. Theorems are tautologies. To show something's a theorem, you just show it's a tautology, and then it's a theorem. So I'm saying here is a theorem of logic. So if P and Q are propositions, then this expression is logically equivalent to this expression.
Okay.
And that's what we're going to prove. You good with what we're trying to show? So let's fill it out real quick. So I need to build up this expression, and I need to build up this expression, and then I need to show that they're logically equivalent. If this is always logically equivalent to this, then this logical expression is always true. Let's start filling it out, and then we'll go back to stressing it. So I know to build up this set, I'm going to need a not Q and a not P. So first off, my P's and Q's, what are all the values that they can have? I can have true and true, true and false, false and true, false and false. Those are all the possible combinations, right? Well, if P is true, then not P is
False.
false. We'll do column at a time instead of row at a time. If P is true, not P is again false. If it's false, we have true and true. Good with that column?
Yeah.
We're just doing the negation of this column. This is P, so this is not P. Now let's write not Q. If Q is true, not Q is
False.
then,
True.
then,
False.
then.
True.
Once again, this is just a negation of this column. Right? This column's Q, all the values that Q takes on. So not Q would take on those values. Alright? So let's write out P implies Q. So true implies true is
True.
true. True implies false is
False.
false. False implies true is
True.
true. False implies false is
True.
what is it?
True.
True. If the antecedent is false, the implication is vacuously true. Always. Right? Okay. And then let's write down this one. Not Q implies not P. So now I'm doing this column implies this column. So false implies false is
True.
true. True implies false is
False.
false implies true is
True.
true implies true is
True.
true. Now I could have written out one more column. I could have done this and written out one more column that had this big beast on it.
Yeah.
Right? So let's pretend that I put this, we'll put star to represent this, and let's pretend I put star right here, and let's look at it real quick. So now that's saying this or this column is logically equivalent to this or this column.
True.
True is the same as true?
True.
Yep. False is the same as false?
True.
Well, true, 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 true. Right?
True.
So typically when we're doing these proofs with, these are called truth tables by the way. Typically when we're doing proofs with these truth tables, we don't bother with this last column. We just get down so we can see, oh yeah, those two columns are the same and we call it good. It's very rare that we take that, write that, and that's there, and then see that's always true. So from here on out, I'm not going to bother with this. Make sense?
Mm-hmm.
All right. You getting tired, James? Quit it!
I'm getting tired of people, of course.
You're getting tired of people. Wow. Okay. So let's do it. Well, should motivate why we did this proof to begin with. So sometimes it's helpful to think about an implication this way. So this is P implies Q. This is not Q implies not P. We call it the contrapositive. And even though you don't see this as an implication, I'm telling you down the road, all proofs that we're going to be doing are implications. And so sometimes, rather than think about the implication, it's easier to think about it this way. So now let's make intuitive sense that these are the same with some English. If I'm wearing shoes, then I'm wearing socks, is logically equivalent to if I'm not wearing socks, then I'm not wearing shoes.
Yeah.
Let's do it with the oxygen and fire. If there's if there's fire, then there's oxygen, is the same as if there's not oxygen, then there's not fire. Good?
Yeah.
Contrapositive. Those are the same. So sometimes it's helpful to think about an implication this way. Sometimes it's helpful to think about this way. When to use which, it's kind of just art that you develop as you get used to proving. So let's do another one. And this time I'll motivate it before we do all the proof of it. This is showing that not P and Q is the same as not P or not Q. If I don't have both, then I don't have one or I don't have the other. If I'm not holding a red and blue marker, then either I'm not holding a red marker or I'm not holding a blue marker.
Okay.
Right. Intuition clicking a little bit? Do I need to keep making up sentences? Or should we just fill it out?
It's the exclusive or, essentially.
It's the exclusive or, essentially. No.
Isn't it?
She's saying you can't have both, so you can't have both of them be true.
Well, we wrote.
This is saying at least one of them is false.
But you can't have both of them be true.
Oh.
Exclusive or is saying one and only one is true, and one and only one is false. This is saying at least one is false. It's saying this is false or this is false. We have not this or not this.
Okay.
Alright? So let's fill out the truth table real quick. So I'll start with not P. Yell it at me.
False.
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 True.
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 True. Not Q.
False. True. False. True.
It's quite the yell. Okay. Now we'll do P and Q. So we're anding these two columns together. What do we got?
True.
False.
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 Wonderful. And now we're going to do the negation of P and Q. Not P and Q. So we're just going to negate this column,
False.
False.
True.
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 which we know this is exactly what we meant by NAND. So not and is the same as NAND. Oops. NAND.
There you go.
False, true, true, true. When you have them in the same order. We happen to do it in the same order. I probably shouldn't do that so you don't rely on that. Anyways. So let's see. We were trying to show that this is logically equivalent to this, so let's fill this one out real quick, and don't just read this column, actually think about it. So not P, or not Q, so false or false is?
False.
False. False or true is?
True.
True or false is?
True.
True or true is?
True.
True. Remember, this is the inclusive or, it means at least one. At least one is true.
Mm-hmm.
So in these three cases, at least one of them was true. In this case, it was not the case that at least one of them was true. And there we go. So not P and Q is not P or not Q. One way that we might say that is if you want to distribute the not over an and, it gives you ors. Not P and Q is not P or not Q. So when we distribute that operator through, it switches that to that.
Okay.
Good? And we're going to do a similar thing now down here. We want to show how to distribute a not over an or. And, luckily for us, it's going to be an and. So not P or Q means we don't have P and we don't have Q. If we don't have at least one, then we don't have either.
Okay.
If we don't have both these true, then we have this false and this false. I don't know. I'm trying to come up with a bunch of ways to say the same thing.
How is it different from the one before?
This one?
Yeah.
She's confused.
This one was distributing not over an and. Not P and Q.
Oh, not or. Okay, there it is.
And now we're distributing a not over an or.
It's like a game of spot the difference.
I don't know what that is, but. Okay. So, this time we're not going to spoon feed you doing all the middle steps in between. We're going to expect you to just be able to make the leap. So P, so true or true is true, and then not it. Is that too much algebra? Next case. True or false is
True.
not it.
False.
False or true is not it. False or false is not it. There we go. Okay. And then this one's going to be easy. We can just and the negation of both these. So false and false is. False and true is. True and false is. True and true is. Do you all understand why I was saying the opposite of what I had here? Because we're doing not P and Q. This is P and Q. Not P and not Q. Sorry, this one. Good? Okay. So, well, make this last statement, then we'll go back up. Kind of. Let's first make sure. So the ones that we're going to care about from here on out. So these are the ones that we need to make sure we hammer on. From here on out, the ones that we really care about are going to be the not, the and, the or, the implies, and the logically equivalent. Okay? So those are the ones that we care about from here on out. The rest of them we kind of just threw in by way of example. You might think about, well, we've only gone over unary operators and binary operators. What about higher level operators? So, well, I'll just read it. All operators, from here on out, any higher level operator, or any of these operators, or any of these operators, every logical operator, all operators, can be constructed from just the Nand operator. So, if any of you ever go on and get a computer science degree, one of the things you'll be required to do is to build basically a mini computer circuit, arithmetic logic unit, something capable of doing basic logic and adding numbers together, basically arithmetic. And all you'll use is this operator.
Yeah.
So it's in some way, what am I looking for? Basic, primitive operator that you can build all other logical operators from. You can even build addition from just this operator.
But
So
you can't build not or and implies from it.
I can build anything you want from it. So we'll do examples real quick. So it turns out all other operators can be constructed from just a NAND operator. But we will usually just use not, and, or, implies, and logically equivalent. One more point to make. When we're looking at some algebraic expression, and I were to write something like 2 times x squared plus 3 is equal to 19 minus 7. You have what you call the order of operators. You know that first we apply the exponent, then we would do multiplication, then we would do addition, then we would do the subtraction, then we would evaluate this. So your exponential operator has the highest precedence, and your equals has the lowest precedence. Similarly, this is the precedence in logic. We do our nots, then our ands, then our ors, then our implies, then our logically equivalent. It will feel very natural to use these this way as we do it, but there's the order explicitly written down, and as you see it, you'll see it makes sense. So for example, we already are writing out. So I told you that we can make every operator from NAND. So first off, I'm going to show you how to make the not operator with the NAND. So not P is logically equivalent to P NAND P. Let's look at this real quick.
That's bad.
If P is true, then not P is false. If P is true, then true NAND true is
False.
or not true and true is false. True and true is true, not it is false. Not P is the same thing as P NAND P. Okay?
I'm not getting it.
Huh?
I'm not getting it.
Not getting it. That's right out your table.
Just and them together. And then.
NAND is the same thing as not and, so we'll just look at not and. So I have P, I have, so P can be true or false.
Perfect sense, actually.
And I'm going to be looking at P and P, and then I'm going to be looking at not P and P, or P and P, but it's easier for us to think about this way. So, true and true is,
True.
false and false is,
False.
okay. Oh, I didn't do a not P. Let's stick it over here. Not P. Not true is false. Not false is true. So here's our not P column. And then not P and P is false and true. Ah, they're the same. Therefore, they're logically equivalent.
Weird.
It's incredible.
It's incredible.
So now P is equivalent to P and P.
Yes. P and P is how we would construct the not operator.
That is so messed up.
So let's do another one.
Why are you
Let's
able to
construct P and P.
all logic on that?
So we have P and Q. Sorry, this one's now a binary operator, so we have two variables. So
Why
P-
did we not go over this in logic?
Yeah,
Let's go a little bit to the right, because I think I'm going off the screen.
we never went over the
Yeah, that's a good question.
not and operator. Like that seems
Well,
like we
Yeah,
were-
why
If
did
you
we go over
notice-
that in logic?
So I intentionally am trying to develop logic different than you guys have seen it 100 times, because I thought
No.
2/3, if not my entire class, would be students I had all taught before, and I didn't want to bore you with
the same thing.
the same thing that some of you have already had to listen to 3 times this year. Because if you take my logic class, my discrete math class, and my calculus class, the first lecture in any math class is, let's make sure you know logic. So, yeah, giving you something new. You're welcome.
Okay, thanks.
All right.
In computer science, you only use NAND.
It's not that you only use NAND. It's that if I'm going to build circuits, I don't care if I'm using the same circuit a bunch of times. I want to have to build different circuits.
I understand why it would work that way. Now,
So it turns out we can just use the NAND circuit. So I build a NAND circuit, and then from there on out I can just keep using my NAND circuit. Instead of building a special circuit for not, a special one for or, a special one for,
Why wouldn't you want to build those separate or those special cases?
it's easier to construct them from NAND than to come up with the logic of how to design a circuit for the special logic that you're
he's
doing.
saying literally, yeah.
Because you can use P and P instead of not P.
Right. So instead of trying to come up with a clever way of designing a circuit to do not, I can just take my NAND circuit.
When you say
and use that.
circuit, you're talking the physical composition of how.
Yeah, I'm talking about the actual wiring of circuits.
Right. He's not talking programming. He's talking that's how.
Yeah, I'm talking about the actual hardware of the computer.
Okay.
You look at a circuit board.
You don't need
If
to
you design a circuit board,
create a circuit for not create.
well, when you go and actually create one that you're manufacturing, you're going to be as efficient as you can. But for academic purposes, we just care about producing one. We don't care about being clever and cutting all the corners we can to be efficient.
Okay, I thought you were talking about like a CS, like programming, computer science.
Yes, computer science. You will take a computer architecture class where you are most likely going to be required to construct what's called an ALU from circuits.
Why are we rational beings?
Maybe because we have.
What I'm
spirit
saying is,
inside
since
of
a
us.
child, we were able to
We
perform
need to
all
be
these
rational.
operations in our head like that.
Well, no non-rational being was ever able to ask the question. So,
Chimps can do this.
all right.
Chimps can too do this. They can.
Moving on with the relevant material.
Chips
So-
or chips? Oh, I thought you said chips.
So we have P and Q. What are all the possible combinations? I can have false false. I can have true false. I can have false true. And I can have true true. Right? Those are all the possible combinations for P and Q. What are we ultimately trying to show? We're going to show that P and Q is the same as that messy expression.
Wait, I have a question. Why can you create the and with NAND when NAND in and of itself is using and?
Is negate.
It's not. Here's our definition for NAND.
It's literally for. It's
defined
literally a
just.
table.
Here's our definition for AND. Here's our definition for NAND.
You're thinking of it in
No.
a.
No.
Oh, this one.
Yep.
And NAND. It just so happens that NAND is the same thing as not applied to and it's easier for you to think about that way. but it is not defined to be not and. It is defined to be NAND.
Maybe
This
and
one.
is defined
This is
as
its definition.
Not
right?
and.
And so it's a theorem that this is the same as, we have one up here somewhere, not and. Not and is the same as NAND. That's a theorem. That's not a definition. Make sense?
Okay.
Alright, so we're doing the P and Q. P and Q. And then we're doing the, let's see, this is the one where each one has one of each. P, NAND, Q, NAND, P, NAND, Q. Right?
Isn't it? Okay.
Did I mess up parentheses?
No.
Okay, so let's do P and Q real quick. False and false is
True.
True.
false!
I see why you started that.
I'm holding a red marker and I'm holding a blue marker.
I'm so mad.
No, I'm as far away from that as I can be. False. Alright, next. True and false is
False.
false and true is
False.
true and true is.
True.
Alright, so now let's analyze this whole mess. False NAND false is
True.
true. So false NAND false is
True.
true. So true NAND true is
False.
false. It's only false when they're both true. Think about it that way.
Yeah.
It's only false when they're both true. So it's only false when they're both true. Okay?
Okay.
So false NAND false is true. False NAND false is true. True NAND true is
False.
false. You follow all that? You won't have to reproduce this. This is just an interesting side note. It has nothing to do with the development of our
Why are we
now.
Why is this useful in a proof? Like, why are you use that?
It's not.
You're not useful side note. Or not a useful side note, sorry.
It is a side note.
Interesting side note.
Okay.
But it's about it. Every logical operator can be built off NAND. Find me another operator that can do that.
So false. Let's do the next one. False NAND true, or sorry, true NAND false is.
I have no idea.
It's only false when they're both true.
Okay, it's true.
True NAND false is true. True NAND false is true. True NAND true is
False.
false.
I do not understand.
False and true, this one's going to be the same, right?
Yeah.
False, true, true, and false. It's intuitive that that's going to be the same. Finally, let's plug in true for both of them. True NAND true is
True.
false. It's only false when they're both true. True NAND true is false. True NAND true is false. False NAND false is
True.
true.
I don't understand.
Ah, it's the same.
I thought you were saying this one's true and this one's false. You were saying
You don't understand what?
You good?
Yeah.
Easy peasy. You want to do the next one?
Yes, let's do another one.
You want to do another one? Okay. So let's do the OR. We'll use these same combinations.
PP, QQ, that's good.
So now we're going to do OR. Q's over here. So P NAND P NAND Q NAND Q is what we mean by pure Q and pure science. So let's fill out the OR real quick. False or false is?
False.
False. All right. True or false is?
True.
False or true?
True.
True or true?
True.
Okay. So now let's go over this one. False NAND false is
True.
true. False NAND false is
True.
false NAND false is
True. True.
Wait.
You mean
false.
true?
false.
True NAND.
Now I got confused on that. Restart.
Yeah.
False NAND false.
True.
True. False NAND false. True. True NAND true.
False.
There we go.
Got it.
All right. Next one. True NAND true. False. False NAND false.
False.
True.
True NAND, or false NAND true.
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 How do we know?
It's only false if they're both true. Otherwise, it's true.
Okay.
And if you look to your left.
So are you?
Okay.
All you have to care about is, are they both true?
Then it's false.
Then it's false. Otherwise, it's
The
true.
big one or the little one?
We're doing them all in one go, so I don't have to write a ton of columns. So I'm going to do this one first,
You're doing
then
the
this
same
one
thing.
first, then combine them
And
all.
it's the same for both.
Well,
No, this
I
is
thought-
P and P,
Yeah.
and this is Q and
No,
Q.
I don't.
Right?
Yeah, I want.
Okay, so now we're looking at P NAND P, or false NAND false.
Okay.
True.
True.
True NAND true.
False.
True NAND false.
True.
True. There you go.
Coin got it.
Just watch, are they both true? That's false. Otherwise it's true. Okay, let's move that T up. Okay, last case. Just truths. True NAND true is,
False.
true NAND true is,
False.
false NAND false is,
True.
true. There we go, or. You see? Or, we spelled the long way. Good?
I don't like the names.
They're not intuitive, which is why we don't build logic with NAND. We use the ones that are most intuitive, namely not, and, or, implies, and logically equivalent.
Okay,
Are there
implies
any
is
situations
worse
where
than
you would use that besides?
I have never come across NAND outside the context of building a circuit.
Okay.
But it's a common, for any circuit you're building, NAND, we'd say a NAND gate. You use NAND gates, just like you use any other gates, logic gates. So, very common when designing circuits. Outside of that, never seen it. Other than people mentioning what I just mentioned. But all the circuitry of a computer can ultimately be built from NAND gates. Okay,
But we don't really need to do that.
Is that what they
you might.
ultimately are built from? I mean,
No.
No. In
He's
practice,
saying
we
like
don't
stuff.
do or that big messy way.
so you.
Because we could build a little OR circuit that's more clever, and we're saving on circuitry.
Okay, that's what I figured.
We don't need it.
So our phones are just
Yeah,
consistent
no,
of.
just don't garbage.
Just proof that your phone is smarter than you.
Not quite. Alright. So we did those. Okay, now I told you that we were really doing implications when we're doing proofs, and all theorems are really implications. That's because one way that we'll read this logically equivalent is we'll say it's this implies this and this implies this. If both those are true, then they're logically equivalent. Maybe do a truth table for that real quick. Probably should have done that anyways. So let's see this real quick. So we're dealing with P, Q, P implies Q, Q implies P, and then P is logically equivalent to Q. So let's build our truth table.
Okay, but implies are the ones that suck.
Yeah, so maybe this is good to do just in general. Alright, so all our combinations, we can have true false, we can have false false, we can have false true, we can have true true. Make sure I give it to you in different order so you can't just look over there. Alright, true implies false is, we're looking at this one, true implies false is
False.
false. Now let's look at this one, false implies true is,
True.
okay? And are they logically equivalent?
No.
Next, false implies false is,
True.
false implies false is,
True.
are they logically equivalent?
Yes.
False implies true is
True.
True.
It's
true. And don't back off.
He's predictable.
True implies false is,
False.
their logically equivalent is,
False.
and then finally, true implies true is, true implies true is,
True.
their logically equivalent is
True.
true. So what I was trying to tell you, I didn't write the last one here, but I was saying that P implies Q, and Q implies P, is logically equivalent with P is logically equivalent with Q. So in other words, if I add these two columns together, I better get what's right here, is what I'm trying to say. Does that make sense?
Yeah.
Yeah.
So false and true is
False.
False.
false. True and true is
True.
true. True and false is false. True and true is
True.
true. So this column is a conjunction, is anding together these two columns. That's what we're saying. We're saying P is logically equivalent to Q is the same thing as P implies Q and Q implies P. So it's two implications in one. It's saying P implies Q and Q implies P, which is why we give it a double arrow. Make sense? So when we were doing these theorems, we were typically, when you come across a proof where you have to prove that two things are logically equivalent, you kind of break into two pieces. You show this implies this is true, and then you show this implies this is true, and that's typically how you do it. It's just with truth tables, it's so simple to just show they're logically equivalent that. We don't do it that way. Anyways, so when I say that every theorem is really logical implications, it is. And this just happens to be two logical implications in one. Okay. So that's exactly what we're saying right here. X is logically equivalent to Y is the same thing as X implies, or Y implies X and X implies Y. Right? Now, Y implies X, looking back to a bunch of different ways that we could say that, is the same thing as X if Y. Y implies X means X if Y.
Yeah.
Let's come up with words for that real quick. Let's see. Donnie's wearing socks implies Donnie's wearing shoes is the same thing as Donnie's wearing shoes if Donnie's wearing socks. Oh, I said that
Okay,
backwards.
right.
If Donnie's
Donnie's, which one was Y? Y is I'm wearing
Socks.
shoes. If I'm wearing shoes,
and I'm wearing socks.
then I'm wearing socks is the same thing as
If
I'm wearing
I'm wearing socks if
I'm wearing socks.
It needs
No,
to be the other way around.
if
If
I'm
you're
wearing
wearing socks,
shoes.
you're wearing shoes.
No, you got it.
If you, yeah.
Yeah.
If you're wearing
I'm
shoes.
wearing shoes.
I'm wearing
if
socks.
I'm-
If you're wearing shoes, you're wearing socks. The way you did it before was X was shoes.
Donnie, can you just pull off your shoes so we can see?
That doesn't help.
Hey, Mike.
If you're wearing.
Alright. Let's come back and look at them both right here so that we can write them down so we don't get mixed up. So let's see, oxygen and fire, I guess.
Yes.
If there's fire,
Then
so
they-
X is fire, because it looks like a little campfire, right? There we go, makes a word connection.
Okay.
If there's fire, that implies there's oxygen. If there's fire, then there's oxygen. Is the same thing as there's fire if there's oxygen. It's oxygen if there's fire. I make all the connections, I still mess it up. Ah! Alright. Y is oxygen, X is fire. There's oxygen if there's fire is the same thing as there's fire implies there's oxygen.
Yes.
Right?
Okay.
So, Y implies X is the same thing as X if Y.
Okay.
Y implies X is the same thing as X if Y. X implies Y is the same thing as X only if Y. There's fire only if there's oxygen.
Okay.
Means if there's fire, then there's oxygen. There's fire only if there's oxygen. Means if there's fire, then there's oxygen. So, this is the same thing as X if Y. This is the same thing as X only if Y. So when we want to combine them all together, we're going to read it as X if and only if Y.
Okay.
So when we have X implies Y and Y implies X, we often call it X if and only if Y. So that's another way of saying that X and Y are logically equivalent. From here on out, I'm not going to say logically equivalent. I'm going to say if and only if. And then because we use if and only if so much in math, we use that double if to encode it, that double F if. If and only if, we have a shorthand for that F with if with two F's. Make sense? So from here on out, if you see X if Y, that means X if and only if Y. That means X implies Y and Y implies X. That means they're logically equivalent. Good?
Yeah.
What?
Well, using the example you used with the fire and the oxygen.
Well, those aren't logically equivalent, so that won't help your
Yeah.
intuition.
I was gonna say.
You're 6 if and only if you're double 3. If you're double 3, then you're 6, and if you're 6, then you're double 3.
Okay.
You're 6 if and only if you're double 3. Good?
Great.
Okay. Sorry about all my mix-up.
That's good.
So that is predicate logic in a nutshell. What?
It was propositional.
Propositional logic in a nutshell, not predicate logic. We've been talking about propositions, things that either have a true or false value. Now, we're going to introduce predicates. My words are a mess.
Yes.
You guys need to call me out because I don't even notice I do it until someone says something. Predicate logic now. What is a predicate? Well, first off, a predicate is a proposition valued function of some variable or variables. In particular, a predicate of two variables is called a relation. So, a proposition takes a variable, a predicate takes a variable and constructs a proposition with that variable. So I can look at a predicate is blue. Is blue is a predicate. And I can take some object, apply the is blue predicate to it, and it gives me a proposition. The sky is blue. I applied the is blue predicate to the sky, and it gave me a proposition. The sky is blue. That's either true or false. So predicates take some variable and spit out a proposition. Too many P's. Make sense?
Yeah.
We have a special name for predicates that take two variables, and we call those relations. And relation from here on out is a word that you're going to hear 10,000 times, so make sure you understand relation. What?
You said a predicate that takes two variables. Isn't it a proposition?
No, a predicate, in particular, a predicate of two variables is called a relation. Predicate that takes two variables is called a relation. You're very familiar with relations. You've used a ton of relations in math. A common relation is less than. Less than takes two numbers and gives you a proposition, something that's true or false. Less than, I give it the numbers 1 and 2. So 1 is less than 2 is a predicate, or is a proposition. It's true or false. So less than is a predicate. It's a predicate that takes two variables, so we call it a relation. Wonderful. So this is the less than relation. And that's the exact terminology that you heard when you came across this in algebra. They called this the less than relation. And they told you about the less than or equals relation.
So, later on, are you going to give us a different definition for relation?
Okay, so those of you who are already familiar with set theory, and proper
Well, we were just very used
set
to it.
theoretical definitions of propositions and functions are saying, whoa, 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 you're talking about relation, you're talking about function, and we don't even have sets yet. Which is exactly right. So, you have to build your language of logic before you can start talking about sets. And so we can't use set theory, we can't use our way of capturing a relation in set theory to define how we mean it in logic.
Right.
So we have our notion of relation in logic, and then we have some logically equivalent way of talking about that thing in terms of sets.
Right, because they're really similar, it's just they're represented differently, basically.
Well, once you have set theory developed, then what you mean by relation in set theory is identical to what you mean by relation in predicates, in predicate logic, when you're in set theory though. Predicate logic, set theory. And the way that we can talk about relations in set theory. Make sense?
Yeah.
So it's a more restricted notion. Predicates, the way that we're using them right now, the relation that we're using right now, they can take variables. What's a variable? Where do my variables come from? What set do they come from?
Anything basically.
We don't care. We don't answer that question. That's not what we're interested in. The same way that we're not interested in determining whether or not the sky is or is not blue, we're not interested in determining the value of a proposition. We're just dealing with propositions, something that is true or false. Is it really true or is it really false? We're not interested. We're just dealing with true or false. Make sense?
Mm-hmm.
So this is just something that evaluates to true or false when you give it things that we're going to call variables. Where do they come from? We don't care. In set theory, we'll care. Okay. But I'm glad you brought that up because a lot of you that have come across this before would probably be confused by it. So, where were we? A predicate.
You're on the example?
No, actually.
Oh, yeah. So how do we write generic predicates now? So typically we write a predicate if it takes one variable like this. Whatever we're going to call a predicate, I'm calling it P in this case, and I'm saying it eats up the variable X. So this is a predicate that takes one variable and spits out, so to speak, a proposition, true or false.
What's the difference between a predicate and a normal function?
So
Functions
a function is a type of set. So this is kind of exactly what Levi was talking about. A function is a type of set.
Yeah.
So once we have a definition of a function, then we can come up with a logically equivalent structure that is a function in the sense that you're thinking to capture the notion of exactly what we're talking about here.
Okay.
But we can't build up our definition of a function that we want without predicate logic.
Okay.
So in your definition, you say a predicate is a proposition value function. What does that mean?
When we say a predicate is a proposition value function, we mean whatever variable it eats up, it spits out a proposition.
Okay.
We don't know if we'll cheat for a little bit and use language that we shouldn't and say we don't know anything about the domain. All we know is that the range of this thing is true or false.
So why not? I mean, could you also say that it's a proposition value relation?
A relation we're using specially to say a two variable or a predicate that takes two values. So a predicate takes some number of variables and spits out a proposition.
So in this sense, a function isn't a type of relation.
In this sense, a function is not a type of relation. Correct. Because, well, we won't do that because we'll lose other people.
Okay, go.
We can rehash out this conversation when we define a function, and we can show exactly in set theory a way that we can perfectly capture what we're saying here. But for now, we're just saying it eats up some number of variables, and it spits out a proposition, true or false. Is blue eats up one variable and spits out true or false. Thus, if we put the sky into our is blue predicate, it spits out true. If we put the desk into the is blue predicate, it spits out false. The desk is not blue, the sky is blue. So typically, when we write P of X to be a proposition, we mean P is the name of the proposition, and X is signifying that it takes one variable, X. Right? So Px is a proposition whose truth value depends on the variable X. We could also have a proposition that needs two variables, like the less than relation needs two variables. The less than predicate, the less than relation, we can use both those terminologies because it takes two. So Q of xy is a relation whose truth value depends on the variables x and y. So anything strange with how we've introduced predicates so far? Anything we don't like in those definitions? Good to keep going?
Mm-hmm.
Okay, so in the special case where we have a predicate that's a relation, it takes two values, we often write the name of the relation between them, x, q, y. Instead of saying q of x and y, we might write it x, q, y. So instead of saying less than applies to 1 and 2, we say 1 is less than 2. So when we have a relation, or a binary predicate, whatever you want to call it, then it's very common that we write it in between the variables it's operating on. Make sense?
Yes.
Those of you with logic are probably real comfortable with going back and forth because we did that a lot. So, examples. X is blue is a one-place predicate, right? So we could encode this with B of X, something like that if we wanted, right?
Okay.
X is greater than 2. How many does this take?
Two.
It only takes 1. So this is the greater than 2
Are you asking
relation.
how many variables? Or
Yeah, how many variables does this eat up? Is this a 1 variable predicate? Is this a 2 variable predicate? Is this a 3 variable predicate?
One.
It's a 1 variable predicate. This is the greater than 2 predicate.
X is the only.
So when we plug 5 in, it's true. When we plug 1 in, it's false.
No, the predicate is
Greater than 2 is the predicate.
X is the only. Then how is any of that even a relation? Because here 1 is less than 2.
This is not a relation. It's a predicate. Relation needs 2 variables. This, on the other hand, is a relation.
Why
It
is
takes
X
2
and
variables.
2 not both variables?
2 is not a variable. You know what 2 is.
It's 2.
What's a, you've worked with variables in algebra.
Then 1 less than 2 is not a relation.
1 less than 2. Oh, this right here.
Yeah.
I was showing an example of evaluating a relation. So I'm saying pretend that we're dealing with the less than relation and we're plugging in 1 and 2.
So it's a predicate.
Yeah, so we applied this to x is less than y was our relation. And I'm saying, and we plugged 1 and 2 in there. So now this is true or false because we plugged in numbers. Here it's not true or false. X is less than y, true or false, you can't answer. So this over here is just a predicate. Predicates are not true or false. It's only when you plug in values for the variables that you then have a proposition. Make sense?
Yeah.
So you can't say this is true or false, but when we plug in 1 and 2, now we can determine if it's true or false.
And that would make it a proposition or a predicate?
Yeah, now it's a proposition.
Okay.
A predicate is a proposition value function. So a predicate is something that when you plug in values, you get a proposition. When you plug in values to this, you get something that's true or false.
Okay.
Make sense?
Then that would be a predicate.
This is a predicate, and it's also a relation.
Oh, that's okay.
It's a predicate, it's a relation. When we plug in values, we get a proposition. This is true or false. We can't call this true or false. It's just a predicate. X is blue is just a predicate. It's the is blue. I'm just putting the X there to signify where we plug in the thing to help it read right. Is blue is the predicate. It's not until we plug in a specific X that this then becomes a proposition. Greater than 2 is a predicate. It's not until I plug in a specific X that we get a proposition. X loves Y. This is the loves predicate, the loves relation. It's not until you plug in specific people that we know if this is true or false. X is greater than Y. This takes 2. X, Y, and Z are triplets. This is a 3-place predicate.
What does triplets mean?
Triplets, they were all born together. Triplets.
Why can't we
Birth of logic.
interpret it
Yeah, I
as
meant
a
birth.
one-place predicate? Like just say X is a triplet, just like X is blue. Isn't that what it's saying?
Well, X is a triplet would be interpreted as, how would you say that in a sentence? You would say, when X was born, there were 2 other people born with that person, or something to that effect, to make it a 1-place predicate. Here we're saying, this person, this person, this person were all triplets in the sense that they were all born together. So I mean a batch of triplets. I don't know any famous triplets out there, but if we did twins, then we could do.
Megan,
Wow, I already lost them.
Megan,
Who were they?
Michael, and
Give me famous
Melissa.
twins.
Exactly.
Megan, Michael, and Melissa.
I have no clue who those are.
They're Burnhams.
Burnhams. You guys know who he's talking about?
Yeah.
Yeah.
Okay, whatever names he just said are triplets. That's true for this predicate.
Megan,
On the other
Michael,
hand,
Melissa.
Leah, Laura, and Rhoda are not triplets. It would come out false.
But if you plugged in those names, you'd have a proposition, even though it was a
You'd have a proposition. Plug in 3 people and you have a proposition. It's either true or false.
Okay, I'm saying let's get 3 different sets of triplets, pick one person from each set for X, Y, and Z. Is that
The way I meant this to be is that would be false. So, in the way that you're saying it, you're making me realize I did a terrible job writing this down because I just made it on the fly.
No, she
I
just
have
likes doing that to people.
So, yeah, the way that you're thinking about it, then it could be a 1-place predicate. Okay. Oh, that's what we're saying. Okay, since predicates are proposition valued, we can use logical operators to construct new predicates from existing predicates. What do I mean by that? I mean, if I already know what P of X is, if I already know the predicate P of X, and I already know the predicate Q of XY, doesn't matter what they are, but let's say that we're dealing with some predicate P of X and some other predicate Q of XY, or YZ, thank you. Then I can apply logical operators on them to build new predicates. Because this is proposition valued when I evaluate it, it's going to be true or false. Since this is proposition valued, when I evaluate it, it's going to be true or false. And then I can apply logical operators to propositions, to things that are true or false. So we can build all sorts of new predicates from existing predicates. So if I know this predicate and this predicate, I can define this new predicate to be this predicate.
But only if like Q and P are the same.
No, I'm just saying that's how I choose it to be. So let's say P of X is in the classroom, and Q is sitting next to each other, right? So Peter and Rhoda satisfy sitting next to each other, and in the classroom applies to Leah. So when I plug in Leah in for P and Peter and Rhoda in for Q, then the whole expression P and Q is true. So this new relation that captures this weird notion of this person's in the classroom and this person's sitting next to this person, some weird relation,
In different
we can define in terms of existing relations.
But they could be in different rooms.
They could be in different rooms. And then that has nothing to do with what I have written here.
Okay, but wait.
Let's think about an actual case. Let's think about if I want to do less than or equal to applying to X and Y, I could define that to be the predicate, I could define that to be equals applying to X and Y, or greater than applying to X and Y.
Okay, yeah.
So here's the equals predicate, which takes two things. Here's the greater than predicate, which takes two things. So I can define this new predicate, this new crazy symbol I just made up, that takes X and Y. How do I define it? I define it to be whatever this evaluates to and this evaluates to. And I OR them together. So if this is true or this is true, then this is true.
Okay, that makes sense
Wouldn't
because
that
it
be
has
an
the same variables, but the top one doesn't have the same.
Well, I didn't have to use the same variables, I just chose to. I made one that makes sense in your brain. Oh yeah, you might use that. Here I made one that, yeah, we probably never use it. The point is we can do it. I'm not saying what's useful, I'm saying what we can do. We can apply logical operators to predicates to build new predicates. Because when it's all said and done, predicates just give you propositions. That's all we're getting at.
Okay.
Does that make sense? You look at me a little blank.
Me?
No, the person I'm looking at. No, you. Yes, you. You good?
Yeah.
All right. Let's move on. If you're starting to get burned out, let me know. We don't need to keep pushing because for some of you this is review for the nth time. For some of you this is very new information. So if you're getting burned out, let me know. We can stop and we can pick it up next time. There's no rule that says we've got to go this long, this hard, this fast, whatever. Good?
Good.
Yeah.
So we get to keep going.
Mm-hmm.
After you've done all that writing, jeez. Be ashamed.
Ah, that's nice of you. But it's not good. Because I don't want your courtesy to me to cause you to not learn, which is the whole reason I wrote it to begin with. See? Okay. So next. Next is, well, let's just read it for a second. So let P of X be a predicate, then, so we got some weird symbol that we just put in front of there.
Mm-hmm.
So the way that we read this is for all X, so we read that as for all or for each or every or, I don't know, you guys think of any other ones? I'll most of the time probably just say for all. So for all X, P of X is a proposition that is true if and only if P of X is true independent of X, otherwise it is false.
That's a weird definition.
Can you see it?
For all X, P of X, this is true if it's true for every x.
Okay.
Or no matter what x is. If it's always true, if p of x is always true, then for all x, p of x is true. If it's not the case that p of x is always true, then it's not the case that for all x, p of x.
Agreed.
So we are now taking some generic predicate and we are creating a proposition out of it. So let's look at an example real quick.
Well, it's like the implies one. When your second one is true, it's true. If your x is always true, then it's true.
If p of x is always true, then this whole thing is true. So let's just look at this one. So if I say x is greater than or equal to 2, true or false?
We don't
You can't. Why? Because it's just a predicate. It's not a proposition. But notice if I say for all x, x is greater than or equal to 2.
Then it's false.
False.
That is now false. Because there are x's that make this not true. So since this isn't true for every x, or since this isn't true independent of what x is, then this expression here is false.
Because it relies on x.
Yeah, because it depends on what x is for this to be true. However, if we look at this one, for all x, x is greater than or equal to x.
True.
True.
X is always going to equal something.
Yeah.
Okay?
Right.
So we're now able to take something that was just a proposition before. We apply this, we call this a universal quantifier to it. And when you apply a universal quantifier to a predicate, it then gives you a proposition as well. So we have two ways to turn predicates into proposition. One is plug in values for the variables. That gives us a proposition. Or apply a quantifier.
Okay.
With me so far?
Yeah.
This is the universal quantifier. The other one that we're going to exist is called the existential quantifier. We read this one as there exists. So there exists an x such that p of x, and for every x, p of x are the two ones that we're going to go back and forth between. So anyways, so this one is true. This one is false. Now we're going to get some crazy definition that seems like it makes no sense at all, but it comes full circle. So let p of x be a predicate. Then we define there exists x such that p of x to mean it is not the case that for all x, not p of x. So we'll go over this with English sentences and then come back to definition to make sure it clicks. So if I say that there exists a black swan, so my p of x is black, I'm plugging in swan to that. So there exists a black swan, there exists a swan such that it's black, is the same thing as it is not the case that every swan is not black. If there exists a black swan, then it is not the case that every swan is not black.
Perfect.
Okay.
Is that connecting?
Yeah.
That
Because
makes
this
sense.
is one of the weirdest logical tautologies we got.
That makes sense.
That makes sense? Okay, so if there exists an x such that p of x, then it is not the case that for every x, not p of x. Feel like we're getting that?
Yeah.
We call this thing universal quantifier. We call this thing the existential quantifier. We read this, there exists. We read this for all or every or for each.
You could pretty much read it as true equal to false, and you know that that's
Then it's not.
That's true equal to false.
What? Okay, one second.
Not black. So you can't say every swan is white.
What if every swan was...
because if the
If
second
every
statement
swan's white,
Pick a universe. Every swan's white.
still valid.
Is it true that there exists a black swan?
No.
False. Is it true that it is not the case that every swan is not black? No, it is the case that every swan is not black. You said they're all white.
Yeah,
If they're all white, then it's the case that every swan is not black.
right,
So it is not the case that every swan is not black. It's false.
right. Okay, so choose world, every swan is black. Still
Choose a
valid.
world, every swan is black. Does there exist a black swan?
Yes. Okay. my
Is
whole
it the
point-
case that every swan is not black?
Right.
No. So it is not the case. that
What
every
I
swan
was
is
doing
not
in my
black.
head
Yes.
was, there exists does not necessarily mean
Don't worry about it.
there couldn't be for all.
No, there exists p of x means not for all p of x, not p of x. Or, here's another way that you might want to think about it. There exists x such that p of x is the opposite of this for all x not p of x. Those would be opposites.
Right.
So it's logically equivalent to this thing's opposite or the not of that thing.
That was actually the way I was
Okay.
thinking about
That's the way we did it in logic. We defined it in terms of not this is this. But the way that this book's going to do it, or not this book, the way that we're doing it this way is we only have to define this, and then we can define this in terms of this, which is better. So we good with this one? Okay, moving on to, we already said this. That is the universal quantifier. This is the existential quantifier. Those of you discrete math, I guess we just covered this, huh?
Yeah.
What is existential?
You know what? I'm actually going to pull up those math examples that we have because I think that that helped hammer it home, right?
Yeah,
Yeah.
I think it did.
So let me find some examples from our discrete math book to help.
Grammatically, what does existential mean?
There exists something.
No,
Yeah.
we went
It
over
exists.
quantifiers
It exists.
for all n
Okay,
that
use
exist.
it in a sentence.
It has to do with identity.
Use it in a sentence. Like grammatically.
Right there, where it says there exists a black swan. The
No, use the word existential.
existential? An existential crisis?
That's why I figured.
That's the first thing that comes to mind.
I thought of existential crisis, and I'm just saying
Wait,
there exists a crisis, but as a
there exists something that
No.
Existential
An
seems like saying
existential
a
crisis
super
is
thing.
when you have a crisis about
Do
your
any of you
existence.
guys remember what section it was?
So it's like you're like, why do I
right.
exist?
Existence
When you
of
ask
life.
yourself, why do I exist, you're having an
11,
existential
page
crisis.
51.
But like
If
alien
you want to go over all that much different math, that'd be
Do you
great.
do that?
Page 51.
Very
Well,
Their anxiety is actually.
It's like things.
So it would seem existential that you would promise.
Oh.
Exactly.
James, is that why you're mad at people?
Okay,
At
so
least
let's
for
go
all
over
of you guys.
a bunch of
People.
no.
math examples that you all are familiar with to help cement these quantifiers in your head. So, we just do every possible combination with plus
Plus then.
and then multiplication, always making it equal to 0. Okay, so we have for all x, for all y, x plus y is equal to 0. For all x, there exists y, such that x plus y is equal to
What?
0. There exists x, such that for all y, x plus y is equal to 0. And then there exists x, there exists y, such that x plus y is equal to 0. Okay, let's go over all these. Is it the case that for every x and for every y, x plus y is equal to 0?
No.
No, so in this case, this whole thing is false. Here's our predicate, right? This is our predicate. Drawing it how we've been doing it here, we draw this like this.
Yes, sir.
Something like that, right?
Mm-hmm.
For all x, for all y, x plus y equals 0. No, this is false. But notice it's a proposition, right? So we took a two-place predicate, we applied two quantifiers to it. When you apply a quantifier to a variable, we call it bounding the variable. So if I take my predicate and I bound every variable, it turns it into a proposition. So if we had two, over here we were talking about one place predicates that only had one variable. Here, since we have predicates that had two variables, we need two quantifiers in order to turn it into a proposition. Does that make sense what I'm saying?
Yes.
Okay, so next one. For every x, there exists a y such that x plus y equals 0.
Yes.
Yes, that's what we define negative x to be. Negative x is that magic number such that their sum equals 0. Right? So this one is true. Next, there exists an x such that for all y, x plus y equals 0. False. There is no magical x such that no matter what I add to it, I get 0.
Yeah.
So it's very important to note, order matters very much in applying these quantifiers. So this one is false, whereas this one was true.
If that was a multiplication sign, it would be true.
We'll get to that. Now, there exists two numbers x and y such that their sum is 0.
Sure.
Yeah, true. Alright, so we got false, true, true. Now let's switch to product instead of plus.
Sorry about that.
Now we'll do product, 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 product.
But when thinking about this in your head, when you're talking about the there exists, you're talking about one number. When
Yes.
you're talking about the all, you can have any.
You're talking about every number.
Okay.
Yes.
Wait.
That
Exactly right.
kind of
If you're
helps
dealing
with the
with
order
numbers,
thing.
though.
Yeah,
Huh?
when you
If
were
you're
explaining
dealing
it
with
to us,
numbers.
you said there just doesn't mean it's just one thing.
It means there's at least one,
Yeah.
Yeah. Okay.
right? There exists someone in this room. Yes, there are just many people in this room.
Yeah.
Okay, so good catch. There exists means there's at least one, and for every.
Okay.
Just to look forward for a second. You mentioned, I think when you announced in devotional that you're going to be developing some piano axioms, right? With set theory? Or are you going to use the field axioms and positivity axioms?
Piano's axioms? I said I was going to do that.
Yeah.
I think I said I could do that.
Yeah.
So I didn't say that I was going to do that. We could do that. So we will get set theory up to the point where we could then apply Piano's axioms. And that's going to be a judgment call that the class makes.
Okay.
Because from there on out, you're developing arithmetic.
Right.
So when we're doing real analysis, we're using the field axioms, right?
Right.
That's because we're starting real analysis from, here's the axioms that it's like geometry. Geometry is another example. We'll say geometry because all of you know geometry. Geometry, we pick our geometry axioms and we pick whatever they are. Those, depending on what you're using, Hilbert, I think, says 26 axioms. So you take those 26 axioms and then you start looking at their logical implications. When you do set theory underlies all fields of math.
Right.
So there's two ways that you can do it. You can take the axioms of geometry and develop from there, or you can develop set theory and then build geometry from set theory and go from there. So once I have set theory, I can build arithmetic from set theory. I don't need axioms anymore.
Does it take significantly longer to use Piano's axioms than?
Than to just have, yes, because you're building up to the axioms that you use in real analysis, essentially.
So in topology, are we going to be doing a lot of the same theorems where we prove all the stuff we did in our
So topology, since we're so interested in just sets, and we're not interested in arithmetic and numbers, we're just interested in sets.
So we're not going to be doing that?
We'll get to the point where we have a definition of the natural numbers in terms of sets. Maybe, I think I might define addition and then leave it at that.
Well, the definition we have in calculus is to...
We don't have a definition of addition in calculus. We have the field axioms, which tell us that whatever this plus is, it does this, and it does this.
Is that not the same thing as definition?
No. Your axioms have undefined terms. Remember, when you talk about an axiomatic system, you've got four things. You've got your axioms, your undefined terms, your definitions, and your theorems. Axioms can't use undefined terms. They can only give meaning to new terms in terms of your primitives.
So, whatever axioms we use to... You said we're developing set theory, right?
Yeah, we'll build set theory. We will build a set theory from which you can build any field of math you want.
Doesn't that mean you're going to be using Piano's axioms?
No, that is how you build arithmetic from set theory.
Oh. So do you have axioms in set theory?
Yes.
Okay.
Set theory is just like any other field that you build.
So topology has very little relation to arithmetic and stuff and algebra, essentially.
Topology is the least number related field I can think of. Like when it comes to doing arithmetic, number theory, I don't know. I can't think of like a more opposite field of math. It's dealing with it's the minimal structure we can give to set. So topology is like the most minimal structure I can think to give to a set. I can't think of anything more minimal. So we could go off that way if we wanted to. I left it open that we could because I halfway wondered if any teachers would have been interested who teach math, because then they might have been interested in doing that for.
Well, isn't that what we wanted to do in logic?
I've always wanted to do it, but all of this is stuff I wanted to do.
I've been wanting to go through those axioms for a while.
Yeah, I'm in the same boat as you. So, but I want to do it all, so I kind of just let the students decide. So if you want to do everything, let the students randomly pick what you do in what order. No, they don't. But
I like what I get.
yeah, it's all great. All right, where were we?
You were going over this example. You just barely changed them to timesing.
Oh yeah, we were doing that same. Okay, so let's do it now. For every x for every y, x times y equals 0.
Yes.
No?
False.
False. No. Counterexample, 2 and 3, right? Okay, for every x there exists a y such that their product is 0.
Yeah.
Yes.
True.
There exists an x such that for every y their product is 0.
True.
Yes.
True.
Yes, this time it's true. There exists an x and y such that the product is 0. True. Okay, so there's some using those quantifiers. Hopefully you're getting more comfortable with quantifiers. Yeah, there exists and for every or for each or for all. Okay. Theorem. If p of x is a predicate, then for all x, p of x is logically equivalent to not there exists x such that not p of x. Let's think about a sentence that makes sense real quick. So let's do p of x is swans are black, and we'll do, so let's see, the first one would be every swan is black, right?
Yeah.
Every swan is black.
So there does not exist a swan that is not black.
There is no swan that is not black, right?
Right.
Make sense?
Yeah.
For every swan is black, there is no swan that is not black.
Oh, that's cool.
For every x, p of x is the same thing as it is not the case that there exists an x such that not p of x.
This one makes a lot more sense than the other one.
Yeah, for some reason I just
Like,
made
it's
it
a lot
easier.
faster.
Well, okay. So let's prove it. Let's do our first proof. So, for every x, p of x, we need to show that this is logically equivalent to this thing. Now, when you're showing that two things are logically equivalent, it's exactly what you're used to in algebra. If I give you some crazy expression, I say that this is equal to 6, what do? You take the crazy expression, you keep manipulating it so
Until you get 6.
without changing the value until you get 6. We're going to do the same thing. So we're going to take the more complex of these two, which is this expression, and we're going to keep messing with it until we get it to look like this expression. Now ultimately, big hint, we're going to have to use our definition somewhere along the way. So I'm going to manipulate this, somewhere along the way use this definition, and ultimately get this. That's big picture what I'm going to have to do. Using logic and this definition. And what do I mean by logic? I mean using what we know about our logical operators. That's what I mean by logic. Okay, so let's do this proof. Let p of x be a predicate. Simple enough?
Okay.
How many of you have never proved anything before?
It's been a long time, but
It's been a long time, but you've come across proofs before.
Yeah.
Yes.
Like, I've never proved anything before. Maybe we'll just pretend like you haven't for a second and talk about some big picture stuff when it comes to proofs. So all proofs, I told you, are going to be in the form of implications, if-then statements. If we want to show that an if-then statement is true, when is x implies y true? Let's see where we have it. When is x implies y true? It's true when the antecedent and the conclusion are true, right? Or when the antecedent is false. Okay? So, I've got this if-then statement. When I don't have a predicate, then the statement's true. So all I need to show now is that when I do have a predicate, when the antecedent is true, then the conclusion is true.
Which you assume you do.
Antecedent is the first one.
Is the first part. The antecedent, the condition, help me out with those of you who have terminology. The X. I don't know. Yeah, when the first part is false, we don't care. The statement's going to be true in that case. So when we're doing a proof, all we care about now is showing that when the antecedent's true, then the conclusion's true. That's the only part that we care about showing to prove the whole theorem. When the antecedent's false, it's true. Okay, so we don't need to worry about that. What about when the antecedent's true? Is the conclusion still true? If that is the case, then we've proven that the statement is always true.
Okay.
Or, another way to think about it, if what I said to you makes sense, good. Now I'm going to say the same thing a different way, so don't let me confuse you by saying it a different way. Another way that we can show that x implies y is always true is to show that it's not false, right? So if I show that when the antecedent is true, then the conclusion is always true, then it's definitely not the case that when the antecedent is true, the conclusion is false.
Okay.
So if I show this being true, shows that this column is always true, then it can't be false. This case can never come up. Therefore, it's always true.
So
There's
the way-
another way to think about it.
Okay.
So when we are doing an if-then proof, here's the way that we always do it. We assume the antecedent is true and show that implies the conclusion is true. So I'm going to assume this and show that implies this, and we're done. It's always true.
Okay.
If every time this is true, then this is true. If that statement I just said is true, then it's proven. We're done. Am I
Does that
stressing this too hard?
No, that makes sense, because you've already limited what your outcomes can be because you've taken away the first two false options.
Right.
Because you're saying let the first statement be true.
Let this statement be true. Yeah, we're going to assume that this is true. Show that this being true.
Then it's-
Therefore, it's a tautology. If every time the antecedent is true, then the conclusion is true, then it's a tautology. It means we never got the antecedent true and the conclusion false. We never got the false. So if my implication can't be false, it has to be true. Good?
Yeah.
So the first line of your proof is always going to be something along the lines of let my antecedent. If P of x is a predicate, okay, let P of x be a predicate. P of x is a predicate is my antecedent. Let my antecedent.
Okay.
Make sense?
Yeah.
That's a very common way that you do the first line of your proof. The way we typically do the last line of our proof is therefore my conclusion. Therefore this.
It's true.
Right? So I could cut my proof, even though I don't really need it. We'll come down and we'll write that just for the sake of showing that this is a general pattern that we follow in proving. Therefore, for all x, P of x is logically equivalent to not there exists x such that not P of x. And then we put a little box at the end of it. Why a little box? I'm not 100% sure why a little box. It used to be the standard that at the end of every proof they would put QED, which was, what's it called?
It was.
When each letter represents a word.
Acronym.
Acronym, thank you. It was an acronym for some Latin phrase that meant something to the effect of, and thus it is demonstrated, and it slowly evolved to squares from now. So every proof at the end has a square, signifying the end of the square, which is roughly supposed to mean, and thus it is demonstrated. Okay, so, proof. First line, assume the antecedent. Last line should always be therefore conclusion. And now we gotta connect the two. Alright, so let P of x be a predicate. I'm going to define this new predicate Q of x to be not P of x.
Okay.
Okay? And notice that that means not Q of x is P of x. If I not both sides of this, I get this.
Okay.
I'm using equals when I should be logically equivalent. Sorry. That's not good. Logically equivalent. Logically equivalent. Because we haven't defined what an equals is. One more note that I should have made forever ago. When I'm doing examples, I'm going to pull stuff out from anywhere. I'm not going to make my examples limited to just the stuff that we've proved just in this class. So all my definitions and all my theorems will slowly build off of each other, but my examples can come from anywhere, they can be anything. So while we did use equals, I'm not sure where, but we've talked a lot about equals in terms of our examples just to help establish your intuition. You shouldn't allow me to use equals in a proof like this because we have not defined what that symbol means. We know what these symbols mean, and that's it.
I'm not gonna lie, no, stop.
Wow, that just makes me want to throw stuff at you.
I can be super annoying.
Logic after F.
Then be super annoying.
No.
So you lied?
No.
You can be?
I can.
Prove it. Okay, let's see. So back to our example. So if Q of x is logically equivalent to not P of x, then the not of both those is going to be logically equivalent, right?
Yes.
I'm kind of doing a lot of algebra in a few steps because I ran out of space. So applying not to both sides still gives us logically equivalent things. And not P of x is the same thing as P of x. Or in other words, not x is just x. Not true is true, and not false is false.
Two negatives.
Is that enough of a... Can we follow that, or is that too much of a leap?
No, that makes sense.
Makes sense.
We're good?
Yep.
Okay. So you're good with if Q of x is logically equivalent to not P of x, then not Q of x is logically equivalent to P of x.
Yes.
And this is just to help see how we use our definition. You'll see. So what I tell you I'm going to do. I told you I'm going to take this, and I'm going to keep manipulating this until I ultimately get it to look like this.
No, dude.
Yeah.
You take your more complex and you keep manipulating it to make it look like you're simpler, and you're done. So that's what I'm going to do. So I start out with my complex messy expression, right? Well, not P of x, we know, is Q of x. So going from here to here, that's all I did. Why did I do that? Because I have a definition for this. There exists x such that Q of x. There exists x such that some predicate involving x is logically equivalent to this. So I'm going to substitute. There exists x such that Q of x
Without the not, right?
into, the not's outside. So ignore the not. We're just substituting this part of the expression. So this part of the expression is everything inside the square brackets. Not for all x, not Q of x. Do you see how that's using that definition?
So in the first of it, did you purposely change it from exist to all?
Yeah, I'm using this definition. I'm taking something that looks like this,
Yes.
and I'm replacing it with something that looks like this.
Okay.
I'm using this definition. That's what definitions are for. It's for replacing one word with these words. Replacing this expression with this expression.
That makes sense, because if there exists something that is Q of x, then not all are not Q of
It's
x.
good that appeals to your intuition, but what's crucial here is even if it didn't appeal to your intuition, we're just using this definition.
Right.
Because, as you guys know, from those of you who did logic, oftentimes we're doing things like, what is it? We don't know. We just know that this relationship holds. We just know that whatever that is, it's the same as that thing.
We can do it.
I have one of them, therefore I have one of them. Right?
Well, it's the only way.
That's how
I
I
mean,
survive.
not every
That makes
step
sense.
is self-scripts are all.
That pretty much is what a tautology is. Like, you can have any interpretation you want. It's so true.
Well,
Yeah, that
it
has
proves
to do with the...
intuitive. Every step along it.
Sentential interpretation.
Intuitive.
Anyways. So, are we good with going from here to here?
Yes.
Yeah.
Anyone confused by that?
No.
Because this is crucial. We're just using a definition, and you need to understand how to use definitions. Okay. Now, two steps in one. Not, I'm basically putting these nots back together now. Not for all x, not Q of x, is going to be just the same thing as for all x, not Q of x, right?
And not Q.
So the two nots cancel each other out is one way to say it. And not Q of x is the same thing as P of x. So the nots cancel out, so they're not there anymore. And then not Q of x is P of x. Therefore, this is logically equivalent to this, is logically equivalent to this, is logically equivalent to this. So this and this are logically equivalent. And we're done. Good? So there's our first real proof. This type of thing that we did right here, if you don't like this, you're not going to like the rest of the class from here on out. This is how everything is from here on out, basically. It's proofs, 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 proofs. Definitions come along the way, and then we use them. And we create more theorems, more definitions, more theorems, more definitions. That's what developing math is. These are the few assumptions that we call axioms, and then we just look at all their logical implications. Once we have a sufficiently complex structure, we wrap it with a definition.
only did definitions here. We did not establish a single axiom.
No, there are no axioms for logic.
Yeah, we're doing logic.
We're in logic.
I understand
That
that
is the first time we have
that
axioms.
it literally can all boil down to truth tables. If you want to know, okay, what's predicate? Well, predicate deals with proposition. Okay, what's proposition? Oh, it's a statement, true or false. Okay, what's true or false? It's right there. Oh, there are 16 tables, and look at these unique properties. True or false can only be true or false these a certain amount of ways, and then find that right column. Oh, looks, that's an or, that's an and, that's an implies.
I don't think anyone's following you.
No one is.
I'm literally talking to myself.
He's just
Alright.
being mindful.
Well, whatever epiphany you just made, wonderful.
Well done.
Okay,
God lives.
so. Da. Let's see, let's see, where's my proof? And we already did an example to make this make intuitive sense. I had an example after the proof. We already did an example of that. We already talked about how the order of quantifiers matters. Okay, so we have one more definition, and then we'll be ready to start developing set theory. Let's just get
Oh
this
yeah, we're
basic
reading about
definition.
set theory, aren't we?
Yeah,
Are we
so
starting?
that was all the
Tonight?
logic that we were going to develop.
Yeah.
Tried to do it in a very short, fast-paced way. Obviously not near as good as we did in the logic class. For those of you who want more on logic and you want to develop it from the ground up in a much more thorough way, I have YouTube videos.
That was honestly a freaking fun class.
Yeah, but something tells me watching the YouTube videos aren't going to be quite the same as
Being in the class.
attending it.
Yeah.
I wish I had known about that one.
I'll most likely be doing classes non-stop, so after this, chances are we'll do another class. So,
But no.
they really want to do Western philosophy or physics. So, it's like that's the way it's leaning.
Ignore abstract algebra.
Yeah, screw you.
I'll do whatever you want. I'll do abstract linear. I don't care.
Hey, we'll do
It's all fun for me.
I'm here for physics.
Don't go on trick.
We'll see we'll see who's even here when this class is over. And
You're
then
taking
we'll go
We
from there.
know what we're
calculus,
doing
not
next.
trick.
My last definition.
We're like, this is.
I did it the other way
You're
around.
not actually on
This is
use.
accurate.
Well, his.
His isn't used.
If you go application, then you're using sine, cosine.
I know.
Where are you? Oh, it's right there.
You know we need it.
I'm down to do trick.
I made it through trig by the hair of my chin.
Do it. See?
And actually love
Trick was a horse memorization.
Yeah.
More than it was. Like, actually.
Well, if I could find a good trick book, we could also do that. By the way,
How many times is that?
I think one of you guys said that you were going to send me a good trick book. Am I misremembering?
I said I could look for one if you want me to.
I can get you the
I
one that
said
itself
I-
uses.
No.
I don't want one self uses, I know that.
I said
I've yet to
I
find a
found
good
some
trick
that were
book.
better than
Well.
others, but they're still not doing what you want.
Okay, well, if anyone knows of a... Would you understand what I meant by the word rigorous? I want a rigorous trick book.
Oh, okay. Yeah.
Starts out
ours-
with basic assumptions, builds some definitions, builds its way up. In other words, a trick book should probably start with something along the lines of a definition of pi. I'm guessing it's somewhere we'll be able to start with.
Trig originally.
Huh?
You developed trig.
I don't know if there's a person that used
How
it.
do you
They
define
are the father
pi?
of trig.
Because what I'm wondering is there has
Circumference
to be,
over diameter.
Oh, yeah.
there
Well,
has
that's
to be
true. That's
some
kind of circular
sort
reasoning.
of
It's not circular
original
reasoning.
textbook.
Because then it turns out that a lot of things are that ratio.
Stupid.
That is so messed up. That is so messed up.
That's messed up. We know the length of things. We know the lengths of curves. So we have the length of this curve divided by the length of this curve.
Okay, that kind of.
That ratio. There we go. That's what we mean by that fancy symbol.
So proud.
And it happens to have a numeric value that approximates 3.14159, blah, blah, blah. That's a nice side effect.
Length of the radius, right? Oh.
Circumference over diameter.
Yeah.
We should do a trick course.
Diameter is 2 times radius.
What?
You need to
Yeah.
go back and do geometry.
Anyways, let px be a predicate.
That's not.
We should do a trig one. Trig is
Nah.
fun when you don't have homework.
I was just wondering why, I mean, he wrote it because it seems like there would be a textbook like that, like Euclid did the elements.
Well, yeah, there's got to be something. I mean,
Has to
trig is rigorously developed.
Never had.
I just need someone who does it.
I think
Instead of just saying, here's a nice function, here's what it does, here's a nice function, here's what it does.
Yeah, the issue with Sophie's, it was very concrete. It didn't go into the theory a lot, it just went into what.
Is the issue with almost every math class you take.
What you need to do is find a
Bunch of garbage.
professor online.
I already did.
You did?
But we should do
Not
trig if we
always.
get a decent book.
Just always.
I'd love to, I can find this book. Then we define,
Homework is the only turn
Because
off
there'd
for
be a
taking every
professor
math
at
class.
some college who taught.
like for me.
Oh, I understand. Oh,
Peter,
you're,
go read.
you're not wrong.
What?
You're right.
And overnight.
It's overnight,
Well, no.
sleep
night.
probably, and read.
And M's too.
Yeah, I watched him get into his.
With 50 on me.
50?
Yeah.
Last I checked, it was like 0.
So now I'm getting worried. He started playing. So what am I gonna do? No, he's not gonna get class without me beating it.
He's probably gonna get classes.
I'm going back. 22 days. A division week.
Fine.
No. Division week is not hard.
Bro, it's getting gold. It's getting gold. I'm
No.
trying so hard, I don't wanna just go here and talk again.
You're not. Again, I didn't mention your name.
Yeah, I wrote us a reason why he came up with the
alright, let's wrap our heads around this last definition and then we'll be done for today.
Yeah, with the explanation.
Yeah, the explanation point. So let px be a predicate, then we define the unique existential quantifier by there exists a unique x such that p of x. Another way to say it is there exists one and only one.
Oh, okay.
So, for example, there exists one and only one x such that for all y,
X times
y equals 0. Or, yeah, in this case, it's the only x that always satisfies this is 0. But you were thinking about equal to 1, but then you have to specify how 0. I also could have done it this way. There exists one and only one x such that for all y, x plus y is equal to y. And that's the 0,
No.
the additive idea.
What I was saying is X times Y. Or now you got me. X times Y equals X. Meaning Y is the number 1.
Oh, yeah. That worked. Okay, so there exists one and only one x such that for all y, x plus y is equal to y.
0.
There's one and only one number, x, that satisfies this. That's what we mean by there exists with an exclamation point. There's one and only one. There exists without the exclamation point means there exists one. When you put the exclamation point there, it means and only one. So there exists one and only one x is how we read that. Or there exists a unique x. So let's make sense of its definition here. Let px be a predicate, then we define the unique existential quantifier this by, sorry, this is definition. Okay. By one of two things, well, let's wrap our head around it. So if there exists one and only one x such that p of x, then that means that there exists an x such that p of x, right? And what this is going to say over here is that, and if p of x is true for any other things, it turns out they're the same thing, namely the one x that satisfied this. So that's high level what it's saying. If I show that anytime two things satisfy p of p, then they're really the same thing. So if I know that there's at least one thing that satisfies p, and anytime there's two things that satisfy p, they're really the same thing,
Oh, yeah.
then there's one and only one thing that satisfies p. That's a high level way of saying this. So now let's get down to the nitty gritty. It's logically equivalent to there exists an x such that p of x, and for any two things, remember y could be x in this context. For any two things, for all y and z, for any two y and z, for every two y and z, if p is true for y and p is true for z, then y and z are the same thing. Okay,
Weird
now
way
we
to
introduce this symbol, and so equals, when we use it, we do not mean that they have the same value, we mean that they are the same, they are identical. We are talking about the same thing. Does that make sense?
Yep.
Mm-hmm.
So now we're using what we would call first order predicate logic with identity. And I don't like that. I just threw that in there without going over identity outside of that. I should have come up with a way to do that. That's not good. I didn't realize I did it. So we did introduce identity. What do we mean by identity? We mean that they're literally the exact same. We're talking about one and the same thing.
So why can't it be?
You have two names, don't you?
We don't mean that they both happen to be true or they both happen to be false. We mean that they're identical. They are the
How is
same
that
thing.
different from logically equivalent?
How is that different from logically equivalent? Try and come up with a good.
Me and Donnie have logically equivalent heights, but we're not the same person.
Well, when you look at the other definitions that we have, where we're talking about two things being logically equivalent, they're not the same thing, they can just equal the same
Yeah,
thing.
they're
Yeah,
they're both.
I can have two completely different propositions that both happen to be true and happen to be false given the same input, but that aren't close to the same thing.
The value.
I don't have an intuitive way to make it different to you yet.
He used to say it's two brothers that are called.
Anyways, so this is our last new definition. There exists one and only one,
Mhm.
and that's where we'll end it for today. So you should now know what a proposition is, what a predicate is, what a relation is, and what these three quantifiers are. There exists for every, and there exists a unique. Is that all the definitions that we covered? I think that's all. All this will be on YouTube.
Yeah, that's fine.
So the lecture will be up by the end of tomorrow, hopefully. Turn it off now.
Donnie, are you 5'9"?